Friday.
Well, I'm recording right now. What do you need? Just talk to me at the end. All right. So 5.3 exponential functions. All right. So we're moving on. So we're looking at all the topics for today. So best thing to do is let's just make sure we know real quick, just a brief review of what exponents are. So if I write down this 2, how's that read first of all? How do you say that? 2 cubed, 2 to the 3rd power. 2 is the base, and the number up there we know is the exponent. Now what does it mean? What is it telling you to do?
Multiply the base by itself 3 times.
That's right. Multiply the base by itself 3 times. All right, so just a quick remembrance of those rules, okay? Now, so what we're going to look at in particular are exponential functions today. Something like this, like 2 to the x is an exponential function. And we're going to look at its graph. You guys are going to create the points for it. And we're going to graph 4 exponential functions. And hopefully we can come up with the idea of what they look like. All right, now a couple of rules of exponents that we want to make sure that we refresh ourselves on. So this rule, what is it if you take, puts the rules over here. What if you take and raise to the 0 power? What is the answer? 1. That's right. So raised to the 0 power is 1. All right, that's a rule. There is a rule that says if you have a fraction to a negative exponent, this is not as popular a rule, but it is a very useful rule. Does anybody know? Because negative exponents are awkward. It's kind of awkward to work with a negative exponent. So the rule says you can flip the fraction and make it a positive exponent. Okay? So for instance, had we had, say we had, so an example of that rule is 3 to the negative 2. Well, I can do 3 to the negative 2. So, because negative 2 doesn't, how do I multiply something by itself negative 2 times, right? So this is technically 3 over 1 to the negative 2. So if you go by the rule, 3 over 1 flipped becomes what? 1/3. So you can make this 1/3 squared. So that's how it works. And then you multiply 1/3 by itself and you would get what? What's 1/3 times 1/3? 1/9. Okay? So these are 2 of the, or this one is, we use this one a lot. This one you may not use a lot, but it's helpful. Okay? I'm trying to think what else. This one, maybe just a quick refresher on these 2. What is the rule if you have same base and you multiply? What do? Add the exponents, a to the n plus n. And just for division, what's the rule if you divide and the base is the same? Subtract the exponents, a to the n minus n. All right. Okay, so we'll just keep those there for now. All right, so here's what I want you to do. You're going to make a t-chart for each one of these. Okay? So you're going to go and plug in these x's and get all the y's. So I just did 4 t-charts in one. So for instance, the first one here would be 2 to the negative 2, which is the same thing as saying 1/2 squared. So hopefully you can figure that out. Okay, and write the answer. Okay? So just showing you what to do with a negative exponent. All right? You're going to get all these. Now, once you get down here, 2 to the first, 2 squared, 2 cubed should be pretty easy. So take a minute and get all those outputs real quick, and then we're going to plot them. And we'll put 4 graphs on one. do we at least have the first T-chart done, the first column, so I can start plotting? So what did you get for, what do you get when you plug in a -1 for 2 to the x? 1/2, so and the first one was what, sorry? 1/4, 1/2. What's 2 to the 0?
1.
2 to the first?
2.
2 squared?
4.
And 2 cubed is?
8.
8. All right, so I'm gonna go ahead and plot these. So -2 1/4 is here, -1 1/2, 0 1 1 2, 2 4, and 3 8. All right, so right now, I've gone ahead and done that first graph. So let me ask you this. If we keep picking 4, 5, 6, 7 on the x's, what's going to happen to the graph? Is it going to keep doing what it's doing? Is it going to keep going up? Yeah. Okay. So as we go right, it's going up. What's happening as we go left? What happens if we pick more and more negatives here? What do you think is happening? It's going to get close to 0. It's never going to reach it because look, let's just say you put in a -10. Let's just say -10. Let's see what happens. So that would be, if we did -10, that would be 2 to the -10, which is 1/2 to the 10th, which is 1/2 times 1/2 times 1/2 times 1/2, 10 times. So it's basically 1 to the 10th over 2 to the 10th. If I use my properties of exponent, right, I can raise each one. So it's 1 over a big number. So 1 over a big number, first of all, isn't negative, right? It's still positive. And it's close to 0, but it's not 0. See, if you did 1, if you did 1 divided by a big number, just say you did 1,000,000. It's going to be like 0.000001, which is a small number, but it's not negative and it's not 0. So what's happening is what Maria said. As it goes left, it's going to get close to 0, but it's never going to reach it. So what do you call that if you, what do you use graphically to show that you get close to something but don't reach? Yeah, just finish it. Don't do the first syllable there. Yeah, asymptote, right? So this graph, you're going to see, has a horizontal asymptote, but it's only like the left-hand side works. The right-hand side doesn't work. So there's the first picture. And then from there, I think you can get, once you get the y's, you can get the other ones. Okay? But the reason it has a horizontal asymptote is because it gets close to 0 but never reaches it. Okay? All right. Do we have the y's for 3 to the x? Does somebody have those?
Yes.
Okay. All right, Hank, give us those.
1/9.
Okay.
1/3.
Yep.
1.
Okay.
3.
Yep.
9. 27.
Okay. So here's what I want you to see is happening. Those are the y's you should have gotten. So the base is 3. Now let's see if you can see the pattern. Look at just the answers. Just look at these numbers: 1/9, 1/3, 1, 3, 9, 27. Does anybody know what's happening to the previous one to get to the next one? Like if I wrote out a pattern, like if I wrote these numbers out like this, side by side. That's right. The pattern is you just keep multiplying by 3, and that gives you the next one. That's the base 3. Is what it means to raise 3 to power. We're tripling, we're multiplying by 3. If you do 1/9 times 3, you get 1/3. 1/3 times 3, you get 1. 1 times 3, you get 3. 3 times 3, you get 9. 9 times 3, you get 27. So that's how you know this is exponential. Okay, you can see that there's a constant multiplier. So now I'm going to try to use a different color here so we can kind of, we'll grab this one in green. So let's see. -2 1/9, -1 1/3, 0 1. So both graphs share the same point, 0 1. Okay, so let's keep a note of that. 1 3 and 2 9, then I'll have to stop. I'll run out of room. So it goes like this. So there's 3 to the x, okay? Same thing's happening as we go left, okay? And the first one was 2 to the x. All right? So right now, for the first 2 that we've graphed, do they look similar? Or is there something similar about them? Is the shape about the same? What is exactly the same for each of them? Yeah, which 0, 1. Anybody know why they share the point 0, 1? Anything raised to 0 is 1. That's why we talked about that. All right. Somebody else give me the points for 4 to the x. What do you have there?
I have, so to make it is 1/16.
Yep.
And then 1/4.
Yep.
1.
Yep.
4, 16, and 64.
That's right. And you can see that they're quadrupling each time. Now, I won't be able to graph all these. I'll probably have to stop at 4. With 16, I'm going to run out of room. So it's here, 0, 1 still, 1 and 4, 2, 16 maybe, 13, 14, 15, 16, way up there. So something like this. All right. So, I want to kill myself here. So what's happening as so what am I doing with the base each time? I did 2 to the x, 3 to the x, 4 to the x. What am I doing with the base? I've made the base what? Yeah, just a very simple answer. What am I doing? No, look at the base. I'm talking about the 3 graphs. 2 to the x, 3 to the x, 4 to the x. What have I done? Added 1, just made that base 1 bigger. So what has happened between each graph with the shape of it? What would you say? As we increase the base, what's happening to the shape of the graph? Skinnier, if I'm thinking of a hill, the hill's becoming what? Steeper. Okay, good. So what, if I did a 5 to the x, what could you tell me about 5 to the x? What would you know about it? All right, very good. What else? There you go. All right. So these all have something in common. So we just want to, we're going to just kind of keep that in mind. And remember, as we go left, they all go to they have a horizontal asymptote. Now, 1/2 to the x is different. So what should you have got for your first answer here? Yeah, it's 4, because look at the rule. If it's 1/2 to the -2, remember what I said, if you have a negative exponent, you flip the fraction, so it'd be 2 over 1, and make it positive, squared. And 2 over 1 squared is 4. So I use that little rule that we talked about. So this one should be 4. What do you get for the next one then? 2. What's about the next one? All right, because 2 to the 0 power is 1. What about to the, what's next? Then what? Yep, and yeah, 1/8. Okay. Do those values look familiar? Yes, where do you see them? Yeah, in the 2, but they're just reversed, right? Okay. Now what's happening? What's happening with the points or the y's? What are they doing now? Decreasing. So let's see, -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4. I'm going to just stop there. So it's doing something like this. And that is 1/2 to the x. Okay. So what is different with 1/2 to the x and the other ones?
Multiplying by the base, you're dividing.
Okay. Well, technically you're not. You're still multiplying. Because look, what's 4 times 1/2?
2.
2. What's 2 times 1/2?
1.
So you're still multiplying. Yeah. But now why are the numbers getting smaller? Then why are we getting bigger numbers? Yeah, go ahead, Allison. Yeah, you're multiplying by a number less than 1, and everything gets smaller. Because, not just because it's a fraction, because let's say it was 3/2, which is 1.5. If your fraction is bigger than 1, then it's going to increase. So the fact that this number is smaller than 1, that's why we get smaller answers. See, all these are bigger than 1. So 1 is like the boundary for an exponential function. If your base is bigger than 1, it grows. If your base is smaller than 1, it decays, is what we say. Okay? So that's the difference there. So, just to kind of summarize this, if we have y equals a to the x, and a is greater than 1, which is what we saw here, it's called exponential growth. And your graph is going to cross at 1, which we saw. And it's going to have a horizontal asymptote like that. Okay? That's supposed to be a horizontal asymptote. It's not the best. Okay? So the horizontal asymptote is y equals 0. Now, let me just use this. If your a is less than 1, greater than 0, so like 1/2, or 2/3 or something like that, then the graph is still going to cross at 1, but it goes like this, and we call that exponential k. Because it's still being, because you keep multiplying by half, so it keeps getting half as big. Okay. All right. Just ring a bell if you had exponential functions before. Okay. Now, a couple of things. What's the domain for each of these? Whether it's growth or decay, what do you see as the domain? All real. What's the range? What did you say for the range? Does it go to negative infinity? What's the lowest it goes? Or tries to go? 0. Yeah, and you don't include 0 because it never reaches it. Okay? That's the domain range. Okay. All right, so let's see. So, a couple of things. Why can't we do 1 to the x? Why is 1 to the x, or can we do 1 to the x for exponential? What are you going to keep getting? 1? That's all right. So 1 is not exponential. So that's why it's either bigger than 1 or less than 1. All right, so you'd always just get 1. Why can't you do a negative base? Or can you?
No,
Why, or then why not?
because you were shaking your head.
Here's what would happen. Think if you try to make a t-chart for this. See if the base itself is negative, not a negative in front, but this is negative. Think if you made a t-chart. All right, if I plug in 0, I'm good, I get 1. Because we know to the 0 power is 1. Look what happens if I plug in a 1. Negative 2 to the 1 is negative 2. But then if I plug in a 2, I get negative 2 squared, which is 4. What's going to happen is it's going to just skip on both sides of the x. It's going to kind of go like this. It's here, then it's here, then it's here, then it's here, and that's not exponential. It just skips around. So you don't get a graph of that, okay? Not an exponential graph. So for exponential, you got to be greater than 0 for the base, and depending on the size of the base will tell you whether it's growth or decay. Now, a couple of questions. All right, I got to erase because I'm just out of room. Are you guys okay? You got these notes? Okay. All right, a couple of questions here. Don't forget all your transformations that we did earlier on basic graphs. So I'm gonna do a transformation. Let's see if you understand what's gonna happen. Just make sure. So let's say we know what 2 to the x looks like. All right, goes like this. What would happen if I did 2 to the x and I added 1 to it? There you go, up 1, and the whole thing would go up 1. So even the asymptote, so that would go up 1, all right? What happens if I did, and I'm not gonna redraw all these, I just wanna make sure you can picture, and you can always type them in where? Calculator, and just look at the graphic. What happens if I did this, 2 to the x minus 3, and I did a minus 3 in with the x? Right 3, just like it would with anything else. So if I wanted to graph this, I would just have to take maybe 1 point, move it right 3, and then redraw it, okay? All right, what would happen if I did this? A negative in with the x, not that flip.
Oh, it does that one.
Yes, that's right. So, yes, about the y. So if you negate your exponent, it's going to reflect about the y-axis.
And then if it's the base one, it reflects across the x.
Well, in front of the base, yeah.
Yeah.
So on this one, look, I want you to see what happens. Notice 2 to the x right now is growth. But if I do 2 to the negative x, it flips this way. Look what it becomes. Decay. And remember your property that I talked about earlier today. If you have a negative exponent, I can flip the fraction and it becomes a positive exponent. So look, if I have 2 to the negative x, I just want to show you that if I flip 2, it becomes, those are the same graph. 2 to the negative x and 1/2 to the x are the same. Okay? All right, so the negative exponent reflects about the y. What if I did, this was the one you were saying. Now this is not negative 2 to the x, this is 2 to the x then negate. That flips it which way? Across the x. So you would take your growth. So instead of having 0, 1, it's going to have 0, negative 1, and it's going to go like that. Those are all your transformations. But the one that we're going to look at that you'll deal most with that affects mainly your graphs is if I put a number in front. So let's pause for a second and look at that. Okay? Let's see how this, I can't find the marker I'm happy with, so I'm just going to start throwing them away. Oh. This one feels like it's got good ink in it. All right. What happens if I do that? What happens if I put a 3 in front? What does that do?
Just makes it wider. What is straight?
I'm the one asking the questions here, Slick. Keep asking yourself the question and see if you can figure out. Let me help you with it. You're thinking, okay? Because at least the wheels are turning, right? You're thinking. Let me help you with this. Forget if that was there. Remember, that is what gives us our what? What does 2 to the x give you in terms of x or y values? When I made your t-chart, this is what gives you your y's. See? That right there. That's what gives you your y's. 2 to the x. 2 raised, pick your x, and then that's your exponent, and that's how you get your y's. So notice that's what gives you your y's. That's exactly what happens. So now it's going to stretch it, but not this way, this way. All right, so if you put a multiplier in front, and what I want you to see is we'll work some application problems. This stands for your initial value. I want to show you why and make sure that you understand. So I'm going to erase these. We've done all these. And I'm going to leave the 2 to the x up there. So notice, if we do 3 times 2 to the x, because of PEMDAS, you got to do order of operations. So when you plug in your -2, it goes there. and then you multiply by 3. So you gotta do this first, then multiply by 3. We already know what 2 to the negative 2 is, it's 1/4. So it's gonna be 3 times that, which would give us 3/4, because it's 3 times 1/4. If I do 3 times, if I plug this one in, it's gonna be 3 times 1/2, right? Because you can see, I already know what 2 to a power is gonna be for each one of these. So that's gonna be 3/2. Now here's what I want you to show you. If I plug in a 0, 3 times 2 to the 0. Do your 2 to the 0 first. What's 2 to the 0? 1, but 3 times 1 gives us 3. So it changes the y-intercept. That's what I want you to see, is that if I put a number in front, okay, it stretches it like you said. So originally we had 0, 1, but now we have 0, 3. And it still has that same shape, it's just stretched more, like that. But this value here, see, so it has the 0.03. This is technically, we call that the initial value. So like if you were, I don't know, what's something that spreads exponentially?
Germs.
Germs, right? Bacteria, disease. This might be, usually the start you call day 0, not day 1. Usually at the start it's time is 0. Maybe there were 3 people infected. Then 1 day goes by. Well, we do 1. 3 times 2 to the first, we get what answer? Anybody? 6, thank you. I didn't want to stand like that forever. 1/6. But 1 day goes by, we have 6 people. Okay, or whatever it is, however it's growing. But that right there will tell you the initial value. See, look, it doesn't matter if I change things around. 5 times 3 to the x. What's the initial value? What's the value at 0?
3. No, 5.
5. Because look, if I plug in a 0, what happens? 5 times 3 to the 0. What's anything to the 0 power? No, 1. 5 times 1, 5. You'll get it in a second. The number in front is the value when x is 0. As long as I don't add or subtract anything on the end. All right, try another one. 7 times 4 to the x. What's the value when x is 0? There you go. Because when I plug in a 0, 7 times 4 to the 0, 4 to the 0, anything to the 0 power is 1. So what do you call that in terms of intercept? What intercept is that? If you get 0, 7, what intercept is that? Y-intercept. That's exactly right. Okay. Couple things. Exponential functions. When do we have growth? The base has to be greater than what? 1. When do we get decay? Or if we take a growth and flip it, right? But that's right. Okay? All right. Anybody ever heard of the natural base? DJ Natural Base, he's over at the club on the Friday nights, no? I'm just trying to see how gullible y'all were. Doesn't that sound like a DJ's name, DJ Natural Base?
No.
No, nobody likes that.
If you become a DJ, that's your DJ.
That's it. Yeah. DJ Natural Base. No. The natural base is E, the little e. And so e to the x is also an exponential function. But if you don't know the value of e, then you don't know if it's growth or decay. So I want you to do this. Go in on your calculator and do in y1 and graph e to the x and see what it looks like. See if it looks like growth or see if it looks like decay. You gotta bring those batteries, Slick. I can just give you a calculator to take on if you want to get the batteries. Because I don't have batteries. No? Yes. I think they're AAA. I don't know. AAA. The skinny batteries. So what do you see? What does e to the x look like? Do you know where the e button is on your calculator? So there's 2 places you can get it. You can do second ln, and that's where the e is. That's one place to find it. And it has an E with a caret there with an exponent. And then you just gotta put the X up there. That's where I get my E. All right, what does it look like? Growth. Does it still cross at 1? Does it look like it crosses at 0, 1?
Yeah.
My computer was acting weird there. I hope it's. Yeah. So if you graph this on the calculator, it still crosses at 0, 1. It looks like this. So this is still exponential growth. And just so you know, E is approximately 2.7. So it still grows. Anything bigger than 1, you're going to get exponential growth. So I just wanted to throw that out there. So if you see a problem where it has that, and you know, that's it. So what if I asked you, could you find y when x is 7? You probably need to use your calculator. So what would you type in to find that? There you go. Just tell us what it is. I have no idea, like 1,000 or something.
1096.63.
So 1096.63. So you just did e to the 7th, and you get it this way. All right, there's more talk about natural base, but I just want you to see that you may get some problems with E, and then that's what it is. It's still growth, looks just the same as what we've had, and it still crosses at 0, 1. Now, let me ask you this, even though it looks weird, what happens if I did 3 times e to the x? What would the y-intercept be? If when x is 0, what's y gonna be? Yeah, still 3, because remember, anything to the 0 becomes 1, 3 times 1 is 3. Okay. All right. I'm going to put a chart on the board. You're going to tell me if you think it's a line or if it's exponential. Okay? Ready? Is it a linear function or is it exponential? What was the key for exponential? What did you notice every time? What's happening? Yeah, but increases how? That's right, by doing what with the base number? That's exactly right. So you're looking to see, and how do linear functions increase?
Same amount.
Yeah, multiplying or what? What's the math you do? You'll remember. All right, so here we go. I'm going to put a chart. You're going to tell me. I was making charts earlier. That's what I do in my free time. Fun, yes. Exciting, no. All right, so here's the chart. So XY. So first question, is it linear or exponential? All right, you're going to answer that. It's one or the other. After that, find the equation. Okay, whether it's a linear function or an exponential function, you're going to find the equation. So, how do you know if something's linear? What has to happen?
It has to be consistent, right?
It's constant, that's right. Either you,
Okay.
yeah, you're right. You either, remember it's constant on the slope, and you're either doing what every time? What's the line either going to do? It's either going to go up or it's going to go down. Well, if you're going up, you keep adding the same amount. If you're going down, you keep subtracting the same amount. So what I would look at is, how do you get from 5 to 3.8? Is it adding or subtracting? What are you subtracting?
1.2.
So when you increase 1 in the x, you decrease 1.2 in the y. Now, for it to be a line, what has to happen? For it to be linear, what has to happen?
Same.
The same each time. 1 to 2, I go up 1. What's 3.8 to 2.6? Negative 1.2. So what does that tell you? What's negative 1.2? It's the slope. Tells you the slope because it's telling you change in y over change in x. Right? Remember the slope. y2 minus, you subtract 2 y's and you subtract 2 x's. If the slope is always the same, it's linear. So that's what I'm looking for, a constant change. Either keep adding or do I keep subtracting the same number? All right, so the answer to this is it's linear because we keep subtracting the same amount. Now, how do you find the equation? Well, what's the equation of a line? Y equals what? Mx plus b. You need what two things? M and b. You need a slope and you need the y-intercept. Do you see the y-intercept? Yeah, what's the y-intercept? Bam, 5, that goes there. You know the slope?
Yeah.
What's this? Bam, done. You gotta put the sound effects in too. That makes it better. Everybody follow how we do that? So that should be new or review? Review. So I'm looking for two things. I'm looking either, do I keep multiplying by the same number or do I keep adding the same number? Technically, I'm adding negative 1.2. If I'm adding the same number every time, then it's linear. If I'm multiplying the same number, then it's exponential. All right. Ready for another chart?
Yes, sir.
Can I erase this one?
Yeah.
Are you guys okay? All right. All right, everybody see how we did that? And it keeps going, it keeps subtracting 1.2. All right. Next chart. So here's how I know it's not linear, okay? Here's all I did. Here, I add 1 to get to 1.5. If I add 1 again, I will not get to 4. I won't get 4.5, so I'll forget about linear. So now I look for multiplication. And I'm looking to see, am I multiplying by the same number every time? Okay, now, same two questions. So now we know the question, is it exponential? All right. Now, if it is, it's going to have this equation, c times a to the x. So we should be able to figure out the equation from that information. So c is the, remember, that's the y-intercept. Remember, a is the multiplier, is what we're multiplying by every time. I'll show you a couple of ways we can figure that out, okay? So, what is it that well, I tried to give you exponential, right? What's the multiplier? What do we keep multiplying by? 3. Times 3, times 3, and so on. So yes, it's exponential. So if we know that we're multiplying by 3, then what does the base have to be? 3 to the x. What does this c stand for? The y-intercept. Remember I told you that was what's that's what's in front, that's what is where your y-intercept is. So notice this 0, 1.5 tells me that my y-intercept should be 1.5. So I know now that it's gonna be a 1.5 in front. Now, let's just say you don't know that it's what the base is. I'll show you another way you could figure it out. But we should know what the y-intercept is by this. So when x is 0, y is 1.5, that's gonna be in front. So whatever the y-intercept is, that's that multiplier. But let's just say, well, I'm not sure what the base is. I'll show you another way you could figure it out. So here's all you're gonna do. Take another point, so we'll take this point next to it. And we're gonna plug in for x and y, and we can solve for the base. We should get 3. I just wanna prove to you that it's 3. So we take a different point and we sub it in. So y is 4.5 when x is 1. And notice I have an a now, and I can solve for a. Whatever I get for a, well, we already know what a should be, but I just want to prove to you what it is. So let's see. Well, first of all, what's a to the first? A to the first is what? A. Well, how would I solve for a? Well, if I'm multiplying by 1.5, how would I get a by itself? Divide. And you get a is 3. There you go. Okay. So now you know the equation. Y-intercept is 1.5, the multiplier is 3. And then you have your exponential equation. We'll do another one like this in just a second. All right. Okay. Got it? So, all right, next one. There we go. So now we're going to find the exponential equation. So I'm telling you now, so we'll call this example like 3. Find the exponential equation of the form c times a to the x. And here's what you know. F of 0 is 4, and f of 2 is 36. Okay? So I've given you what? Let me rephrase. What does this stand for? What is this telling you? Very good. So these are 2 points, first of all. So this is another way. How do you write this as an ordered pair? What point is f of 0 is 4? What's that? That's the same as what point? 0, 4, exactly. And f of 2 is 36 is the same as what point? 236. And this tells you what? That tells you the what? Yes, the y-intercept. And the y-intercept goes where on exponential functions? That's your c. Now you know that. But now you got to figure out your multiplier. I can tell you right now, it's not 9. You didn't do 9 because, see, your x is not 1, it's 2. That's exactly what you did. You did exactly the way I just showed you. And then you solve for your a. Okay? So find c and a. And then once you find c and a, you have your exponential function. You already know c from the start, like you said, c. No, it's not. Shouldn't be. Did you plug a 2 in for x? Okay. So remember, the y-intercept tells you the c. So right now I know that c is 4. But I gotta figure out what my multiplier is, so I'm gonna use this other point. What do I know? When x is 2, y is 36. So in place of y, I put 36, and in place of x, I put 2. So notice it's a squared, not a. So I gotta solve for a. All right, so how would I solve for a? Well, the first thing I should do is do what? Divide by 4, very good. So 9 is a squared. Then how do you get rid of a square? Square root. And remember, your base cannot be negative, so you don't do plus or minus, you just do 3. And your multiplier is 3. That's it. So now that I have the multiplier, I got a is 3, I sub that back in. So my equation is 4 times 2 to the x. That's how you do it. Okay? So if it's 0 something, that tells me my c. Then I use the other point. I plug the x in for x, and I plug the y in for y, and I solve for a. And this is how you find it. We call it an exponential model. It's giving you the equation of the exponential. Okay? All right, want to do one more? Okay, great, good. Here we go, ready? Example, we'll just call this part B. I'll give you another one. Here. So f of x is c times a to the x, and I'm going to tell you this. Here's your 2 points. Okay? Find the equation. Just one more short type of problem and we'll be done. Sorry, no, it's just, I gotta get this stuff done. I'm pretty sure compound interest problems you've done before, so I'm not too worried about them. You may need your calculator, I don't know, I just made this up off the top of my head, so I have no idea what the answer is. Should A be bigger than 1 or less than 1? How do you know? Okay, very good. What's C right off the bat? You know C is what? 6. So I'm going to go ahead and plug that in. Okay? Now I use the other point to find my A. So y is 1 when x is 3. Okay? Yeah. Not pretty. All right. Now what do I do? Okay? So divide by 6. Okay, I can do that. Now what do I do? How do you solve for a? Cube root. You're just gonna have to get, you'll just get a, what do you call it? A decimal. You just use the decimal. So figure out what's the cube root of 1/6. That's how you solve for a. You have the cube root. You just figure out the decimal you get. .55, that sounds good enough. A is 0.55. So now once you have your A, you shove it back in. 6 times 0.55 to the x. So it's almost a half. There's your exponential equation. But they have to give you a y-intercept to do it this way, and they will. They should give you a y-intercept. All right. Last type of problems. Okay? So we can finish this up and you can work. Last type. So, compound interest. sometimes money can grow exponentially. It doesn't grow as fast as you want, but there's two types of formulas that we use to track money growth, and these are the compound interest problems. Okay, so I'll give you the formula, and then I'll tell you what each letter stands for, and then we can go through and work on this. Okay, so the formula is for compound interest, it finds the amount of money after a certain time, P times 1 plus R over N raised to the NT. And then I'll go through and tell you what each letter stands for, and then it just becomes a plug and crank. You plug the numbers in for each of those. Okay? So A of T is your amount of money in your account after T years. So you'll have to know how many years that the money is in the account growing. P, capital, is the principal, which is your initial amount of money. It's your starting amount. So say you put money in an account and you're just letting it sit there and grow with interest. R is the interest rate, but you write that as a decimal. So if I tell you it's 4% interest, don't do 4. You got to do what? What's a decimal for 4%? 0.04. N is the number of times compounded per year. So I'll give you some words and in a second, and you'll have to know how many times a year that would be. Okay? And then of course T is time in years. Okay, so I'll give you a typical problem for this, and then just see if you can plug in the formula and get the answer. So a typical problem would be, we'll call this example 4. $1,000 is invested in an account that pays 5% interest compounded quarterly for 3 years. Find the amount of money in the account after 3 years. All right, so take a second and write that problem down and then see if you know what letter is what. We want to make sure that you know each letter so you plug in properly. Yep.
The one after the 3 and 5 is going to be the other one.
No, initial. P,
Yeah, and then the inside the parentheses.
initial.
No, she's asking, is that a 1 plus n divided by, or divided by
And that's I?
in the equation?
1 plus R over N raised to the NT.
It is a
Just
1.
making sure that was the
Okay.
1 on I.
Yeah.
1. Yeah, 1 plus R over N. Make sure when you do your exponent that it's n times t all in the exponent. Okay. And then in a second, tell me what to plug in. questions, anything you can't read? My handwriting sloppy?
What's the word after compounded?
Quarterly? You don't like my cues? So the question is, how many times a year is compounded quarterly? Quattro, four. Do these problems ring a bell? I think you would have done them
We got
briefly, yeah. It's just, yeah. It's just plug and crank now. All right, so let's go real quick. Tell me, so we're gonna find A of 3, the amount of money after 3 years. What's your principal? What's your starting amount of money? $1,000. So it's like you're gonna put $1,000 in the bank and let it grow. If you can find 5% interest, let me know, because it's not out there. We're not gonna find that unless we go into like bonds and, you know, stuff like stocks and bonds, all that. So 1 plus, what's your interest rate? 0.05. And then N is the number of times compounded. So when it says compounded quarterly, I know a quarter is every 3 months, but how many times are there every 3 months in a year? That's 4. So it's over 4 raised to the 4 times, and then how many years? So your entire exponent should turn into a what? 12. So make sure that when you raise this, it's to the 12. Okay? And then I just call it plug, it's just plug and crank now. Now you gotta do is type it in. Because once you know where each number goes, then it's just, that's how you use the formula. Okay? Any questions on how so how do I know if 1,000 is P? It's the invested, it's what you plug in at the start. Okay? Let's see what you get. Should be between $1,000 and $1,400, $1,500 maybe, somewhere in there. It should be more than 1,000, otherwise your money doesn't grow. So basically, what the bank is doing, they're paying you for leaving your money in the bank, and they're paying you a small amount. And every 3 months, they're paying you a little bit. And they're putting it in your account. And then after 3 years, that money should have grown to a certain amount, and that's what we're going to find. And round it to the nearest cent, because it won't make sense to round to 1 decimal or 3, because it's money, so round it to the nearest cent. All right, who wants to throw out an answer, and then we can check it. Leah, you got one?
1,160.
$1,160.75. Anybody else get that? One person. No one else? So check your work. Either they're both wrong, or they're both right and we're making a mistake. So we need to figure out which one it is. You want me to come look at what you're typing in, I can help you. I can tell you right now, if you're not putting 4 times 3 in parentheses, like I did, up in the exponent, it's going to be wrong. Is that?
Yeah.
Well, I'm just surprised we all didn't get it, because it's just
I got
typing in. Got it?
Yeah.
How'd you get 0.125? I can tell you 0.05 divided by 4 is not 0.125. I would just type it in the way it looks. Listen, here's the thing. Here's the thing. If you just type it in how it looks, all you gotta do now is hit second enter when you get a different problem, and this will come up and you can change the numbers. Okay? All right, everybody good with that answer? All right, couple of questions. So just to save time so you can get to work, what if I say compounded monthly? 12. All right, so I'm just gonna put the word, you're gonna give me the number, 12. Weekly.
52.
52. Daily.
65.
Semi-annually.
Twice.
Annually.
Once.
I can't think of any others, can you?
I'm confused, where would you put those numbers at?
That's your n. The compounded. See, all I'm trying to help you with is, n is the number of times compounded per year. So what I'm trying to help you with is if you're reading and it says compounded monthly, you know n is 12.
Okay.
If it says compounded weekly, you know n is 52. Right? I'm trying to help you with how you know what n, because everything else should be self-explanatory. Right? It's the n that usually students have trouble with. All right. One last formula. It is possible to compound continuously. Continuously means then would have to approach what? If you continuously compounding, continuously multiplying, how many times a year is continuously?
Every day.
More than every day. What's infinity? You're exactly right. So that would mean n has to approach infinity, where you can't plug in infinity. Infinity can't be plugged in, so there's a new formula. So anytime you see the word compounded continuously, compound continuously, my writing is not very pretty, continuously, use what's called the PERT formula. Use your natural base E. If you see compound continuously, use the PERT formula. P is still principal, R is still interest rate, T is still time, but you use the natural base E. Remember DJ natural base on the calculator? So you use that. So let's work the same problem. $1,000 is invested, 5% interest, 3 years, compounded continuously. See if you can plug and crank to do this. Now remember, make sure you put your R times T, and this one is R times T in parentheses. That's your whole exponent for E. And you should get something a little bit bigger than $1,160.75. So anytime it says compound continuously, you use this PERT formula. And we're going to use the same numbers, but just make sure that we get a different answer. Our answer should be a little bit bigger. Got bigger? You shouldn't get the same number, you should get something bigger.
I messed up.
Yeah, it's okay. Yeah, I'm just letting you know your answer should be a little bit more than what you have there. So maybe, I don't know, a little bit under 1,200?
I put 463.
Make sure you're doing 0.05, make sure you're putting 1,000. Your answer should be bigger than $1,160.75. All right, let me look at your calculator though. You're dividing by 3, I'm multiplying by 3.
Oh my goodness, I'm so sorry.
Hold on. That's it. That's right.
What is E again?
The natural base, E, what you get on your calculator, hit second ln. Second ln. All right, so let's see. A equals 1,000 still the principal. How do I get my E? Second ln, E. Then a caret comes up. Caret means now whatever you type is going to go in it. Well, yours might go ahead and do an exponent. And then your exponent is going to be rate is 0.05 times 3. And it should give you the answer. So what was it to the nearest cent?
1,161 and 83 cents.
83.
Where did you get 3 from? Wait, oh.
3 years.
never mind.
1,000 is invested at 5% for 3 years. And then how do you know to use E though? What has to be the word? Compounded what? Yeah, if you don't see compounded continuously, you don't use this. Only when you see compound continuously. I'm gonna stop this because it's gonna take me forever to upload.